So then, here is wrong color. You like the other one? Okay, so there's a function f. Okay. All right. If we want to calculate the average rate of change of the function, the average rate of change is nothing more than the slope of a secant line. So let's just say we want to go from point, on the x-axis, we're going to go from point x, and then we're going to move out some distance. Let's call this delta x, change in x. And so this point right here would just be x plus delta x, right? Okay, so then we've got 2 points here. We've got a point with the coordinates what? What are the coordinates of that point? X. The function is f. F of x. So this one just looks like x f of x. Good. And what about this point right here? Okay, x plus delta x, and then f of x plus delta x, right? Okay. If we want to come up with the average rate of change of the function on that interval, and let's graph that. Oh, wrong color. God, it can't be that. That's too bland. It's got to be a better color than that.
Make it purple.
We're going purple. There we
Oh my
go.
gosh, why would you choose that? Is that blending too much?
Yeah.
How come the y on the second point can't just be f of delta x?
Because if we ever want to calculate the value of the function at an x value, all we're doing is inputting the x value into the function, right? And so if this is the x value, that's what we have to input into the function. Okay? Make sense?
Yep.
Okay. So this represents the average rate of change. The slope of that is the average rate of change. Okay, and we know how to do that. This is stuff that we learned a long time ago. Really, even back in Algebra 1, we talked, maybe not with delta x's and things, but we talked about this concept. Average rate of change is just given by the slope of the secant line, right? So that's just going to be change in y over change in x, which is what for us? What is the change in y? If I draw a slope triangle here, what does that slope triangle tell us for delta x and delta y? I'll just right? So that's just delta x, isn't it? Right?
Yeah.
What's this? How much is it? How much is the height changing? Okay, good. So f of x plus delta x minus f of x over delta x. No big deal, right? Okay? It looks complicated because it's got x's and delta x's, but I can just give you numbers there, right? What if x was 7 and delta x was 3 and f of x was x squared? I mean, we could easily calculate this, right? Just plug it in, right? That would be no big deal. Here's an example, right? If this were the case, if f of x were x squared, and let's say we're going to choose this value down here, we're going to choose a value of
2.
X equals 2 and delta x equals 3. Be no big deal, right? We just would end up with what? We'd get x plus delta x is 5 squared, right?
25.
So I just get 25 minus f of x would just be 2 squared
4, 20.
over delta x is 3. And so I'd get what? 21 over 3 is 7. That would be, in that case, that would be my average rate of change. No big deal.
Just for that.
Just because that's what the function is x squared.
I'm
Right.
trying to find what
Yep.
is 7 mean?
So is your average rate of change just for that one little area?
Okay, so the average rate of change is, you're right, it's defined between these 2 points. It's just the slope of the line that connects those 2 points is the average rate of change, okay? All right, but what if we want to find instead? Let's say we want to find now, we want to know the instantaneous rate of change at this point right here. Okay, that's different, right? How are we gonna, any ideas how we could do that? How could we approximate it? Like, let's say, for example, that I want to, if I want to find, you know, if I want to find the slope of the secant line, or the tangent line, sorry, could I do anything to those points that might make the secant line at least a better approximation? Scoot them closer. Why not? What if I just scoot them closer? So what if we take the left end point and we just scoot it up here a little bit or something? Or even better than that, I'm gonna make this a little different so this will be better. Just hang on one sec. I'm gonna change one thing. You'll thank me for this later. Let's instead, let's try to find the average or the instantaneous rate of change at this point right there. Okay? So instead, how about if I take the right end point and scoot it closer to the left end point? Which is really just the same thing as making delta x a little smaller, isn't it?
Yeah.
Right? Right. You guys quit talking. Right. Quit talking. So we got the right end point, we're gonna scoot up here a little bit. What if we put it there? That's a little better, right? If I put it there, then look what happens to the secant line. Now the secant line gets to be a little bit flatter, and it's closer than it was to the tangent line. What if I want to do better? What can I keep doing?
Get it close.
Get it closer. If I get it way down here, all of a sudden that secant line is starting to look very much like the tangent line. Okay, is it ever going to be perfect? Do we want a perfect answer?
No.
It's not going to be perfect, is it? I mean, it's just not. You see what I'm getting at? It's a great idea, but it's always going to be an approximation, right? Or is it? What could we do? We've studied some things that might allow us to maybe push that approximation. Okay, okay, which means, what are we doing? Yeah, we're taking a limit as delta x approaches what? 0, right? You see the idea? If we shrink this delta x up closer and closer, we're getting, the 2 points are starting to look more like 1 point, aren't they? The 2 points that define the secant line are starting to look more like a single point, which is a tangent line. Now, we can never pick a value of delta x that is going to give us a perfect answer, but what if instead of trying to pick a unique, specific value, we take a limit? We look at the behavior of the function in the limit as delta x approaches 0, right? And then we've done a lot of this stuff. If we explore that process with our vast, growing understanding of limits, maybe we can take this limit process and spit out a function that actually acts perfectly as the tangent, right?
Which is just that one point.
Which is just at that one point. And that's the goal of our whole, the whole process here. That's what calculus does for us, is it gives us a mechanism for not just approximating, but finding an exact instantaneous rate of change of a function. Finding the slope of the curve, in other words, or the slope of the line tangent to the curve. Okay, so what's that going to look like then? If we take this limit, I'm going to leave the picture for a second, and I'm sure we'll draw it again a million times. But if we had the slope of the secant line was equal to f of x plus delta x minus f of x over delta x, how are we going to get the slope of the tangent line? Okay, it was the limit of the slope of the secant line as delta x shrunk to 0, which pulled that second point back onto the first point and made it a tangent line instead of a secant line, right? So that just looks like the limit of f of x plus delta x minus f of x over delta x as delta x goes to 0. Now, control your breathing, take 10 deep breaths, and don't panic. When you see stuff like this is one, I'm not kidding, this is part of being a good mathematician, is just not panicking when things start to look intensely symbolic and abstract. Where'd the numbers go, for gosh sakes? I mean, years ago math was about numbers. It's not about numbers anymore, right? But really, seriously, I mean, just think about this in terms of what this potentially can do for us now. We've come up with a very, very general expression. This will work. We didn't ever specify what the function was, did we? We never specified what x was. We never specified what delta x was. We've done something very powerful. We have come up with a completely general expression for the slope of a tangent line to a curve. This should work in any situation, right? We never specified a single thing. So let's take a simple example and just show how we can apply this general expression for the slope of a tangent line to a specific example of a curve. Yes, ma'am?
So we're gonna use that a lot.
You're going to use that a lot, yes. This is, by the way, what we are going to come to call a derivative, okay? Which is one of the loaded words in calculus. Now, the good news is, I just want to give you a glimpse so you can kind of see the silver lining peeking through the cloud here a little bit. This is important to do because this is a process in calculus that you will repeat over and over again for different kinds of concepts that you're going to develop further in later years in calculus. But we are going to, relatively quickly, come to a point where we are going to be able to replace this process with some very simple algebraic derivative rules that you can apply almost instantly, that avoid all this limit stuff. Okay, so we are going to get to a place where you're not going to have to do this very much at all. We will get to a point in calculus where we don't do much with limits after a while. We replace limits with better shortcuts. But to get there and truly understand it, you gotta kind of know, you gotta go through. I gotta hold your feet to the fire a little bit here. You gotta go through the limit process a little bit because you'll do it again later on when you all get seriously bitten with the math bug, which you're all gonna do. And you're gonna want to go on and take multivariable calculus in college, where you're going to be doing the same stuff for not just a function in a plane, but maybe a surface, or it's not that much of a difference really. The same methodologies and processes that I'm going to build with you guys in here, you can apply with just a little bit of extra. You can apply to learn all this other stuff later in calculus. And so I just want you to kind of know why I'm doing this, and that this is not a waste of time. This really is an important process that you will see again later on. Okay, so let's apply this though. This is a formula. We can take this to the bank. That's a formula that we can just start with and apply to any specific situation. We'll talk about this a lot in calculus and physics. Starting general and becoming more specific based on the parameters of the problem. So let's say now, for example, that we've got the function f of x equals, we'll start easy, x squared, okay? And we want to know, let's find the slope of the tangent line when x equals 3, okay? That's our goal. All right, so suggestions?
Couldn't you plug it into MC Captures?
Well, this is our formula, right? This tells us what the slope of the tangent line is. We've just got to get more specific. Well, what's our f of x, for example? Our f of x is x squared, right? Okay, so let me ask you a question. If f of x is x squared, what's f of a?
A squared.
A squared. What's f of 2?
2 squared.
What's f of the quantity a plus b?
A plus B squared.
A plus b quantity squared. What's f of x plus delta x?
X plus delta X quantity
X plus delta x quantity squared, right? So it's no big deal, right? This is just a pattern that we're following. So if we want to apply this, then the slope of the tangent line is just going to be the limit of what's f of x plus delta x gonna be again?
X squared.
So it's gonna be the quantity x plus delta x squared, right? That's what that is, right? Let's make some connections. So that goes to that, right? Minus f of x, whoops, minus, what's f of x?
X squared
X squared
over 3.
over
Delta X.
delta x as delta x goes to 0. Okay, we even know something else here though, don't we? We even know that the value of x we're looking for is what?
3.
3. Okay, so we can even make that substitution, right? That makes things even more specific. So this becomes the limit of the quantity 3 plus delta x squared minus 3 squared over delta x as delta x goes to 0, right? Agreed?
How do you figure out those X's?
Delta x is a value that we're going to let go to 0. Once again, let's look at our picture again. Why were we doing this? We wanted to draw these 2 points together so the purple secant line became the crimson, I don't know what that is, tangent line, right? Okay? So to do that, we want to shrink delta x to 0 so the secant slope of the secant line is going to morph into a slope of a tangent line, right? It's very visual. We're just going to draw these 2 points together so that the 2 points are going to superimpose and become 1 in the limit that delta x goes to 0.
So delta X will make a difference in the X value?
Yeah, that's all. Remember, that's all delta x means is delta means change it. So it's just the change in the x values between the 2 points, right? Okay? So on to the math then. Well, this doesn't look too bad. It's a delta x, which looks scary, but that just counts as a single variable, right? You've done stuff like this, a ton of stuff like this. How do I simplify this? If I try to evaluate it directly, what happens?
0.
0 over 0, right? So it's indeterminate. More work is required, but what does the more work look like, you suppose?
It looks like it's canceling the exact out.
Okay, I'm gonna have to do that, but how would I simplify this? You actually did. You don't remember this, but you did a problem just like this out of context.
Take out the delta X.
Okay, how though? Okay, but what's going on? What about that?
Back square, back here.
I don't need to. I don't need to here because I don't have anything I need to rationalize. What if I expand that? Good. Okay, here we go. Great idea. What if I expand this? What if I expand out the binomial 3 plus delta x squared? Okay? So we get the limit of what? If I expand that out, what do I get?
6. plus 2 delta X.
3 delta x.
2 times 3 times delta x, right?
6 delta X.
Quick review. What's this? A plus b squared is what?
A squared plus B squared. 2B. 2AB plus B squared.
Good. Okay, quick review. What is, so then let's do this real quick. What is x minus 3 squared?
X squared plus 6 minus 6x plus 9.
Agreed?
Yeah.
Okay. What is a plus b cubed?
A squared plus 3AB plus B
Plus 3ab squared
cubed.
plus
Okay. So what is x minus 3 cubed?
X cubed plus 3x minus 3x.
Blah, blah.
Plus that minus 9 cubed, which is 27. Woo!
Okay. Does that, everybody could, if you took a minute, could negotiate that, right?
Yeah.
All we're doing, right, all we're doing here is just, when we do this expansion, A is now X, B is now -3, right? No big deal, okay? I will show you, not today, but this week, I will show you a trick for doing relatively small binomial expansions. I showed it to you, I think, a while ago. I know I showed it to you back 2 years ago, and you probably saw it last year, but you probably forgot it. Do you remember Pascal's triangle?
Yeah.
Okay, you do remember how to use it?
No.
Not really.
Okay,
I
well,
just-
we'll review it, but just not today. Maybe like some other day this week, I'll do a quick review of it. Anyway, so if we expand this out then, this is like A and that's like B, right? So I'm gonna get A squared plus 2AB, whoops, right here, sorry. A and B, right? 6 delta X plus delta X squared, right? Minus 9 all over delta X as delta X goes to 0. Okay, look what happens. This is not an accident. This will always happen. What is this? What am I talking about? I'm so excited. Ah, the 9s cancel. Now don't laugh. This is an accurate way to describe this. So all of the naked terms have canceled, meaning all the terms left are I guess clothed in delta X's. They've all got at least one power of delta X attached to them, right? Yeah, you don't like that one? So if these are gone, meaning if all the terms, all the constants are gone, I can now factor a delta X out of all the remaining terms, right? Look at this. So I get the limit of delta X times what?
6.
Plus delta X.
Okay, all over
1. Never mind.
delta X, but it's going to be, but Sydney, it's going to be 1 in a second. How come? Because I can cancel, right? Okay, indeterminacy removed. There was the 0, right? Delta X was going to 0, and so the delta X on the bottom is what was causing that darn 0 on the bottom. It's gone.
So our answer's 6.
So now we can, exactly, now we can directly evaluate, and when we let delta X go to 0, our answer is 6. That's pretty amazing. What did we just do? We just found the slope of the curve at X equals 3, right? Okay, how much time we got?
7.
Okay, good, that's just enough time. Now, how many people have goosebumps right now?
Should just stop here.
Right, thanks for being truthful.
No, how shocking this is.
Okay, well, you're gonna have goosebumps on your goosebumps now because we can do something much more powerful here than just this. Okay, I need your attention though, we gotta really focus. I'm giving you a mental workout here, but we're almost to the end. Okay, what if we didn't specify this? Because that was kind of a weak move in a way. By specifying that, we were pinning ourselves down to saying, we want to know on this function, and if I graph it, we know what the graph essentially looks like. Okay, it looks like this, right? We went out to 1, 2, 3, and we went up on the curve to this point right here, and we found at that one place the slope of the curve. Okay, nice, but big deal. Wouldn't it be better if we could instead come up with what we might call a derivative function that would tell us for any value of X we chose, it would tell us what the slope of the curve was? How cool would that be, right? So what do we have to do back here to get to that point? Really, what if we didn't do that? What if we just stopped right there? Exactly. What if we had just stopped right there and we hadn't specified any value of X? Now we did specify a function, because we got to do that, right? It's X squared is our function. But let's go back to this spot. So we were here, right? We had the slope of the tangent line is equal to the limit of the quantity X plus delta X squared, right? F of X plus delta X minus F of X over delta X as delta X goes to 0. The math is no harder. If we expand this out, what does this give us here if we expand out X plus delta X squared?
Plus delta X squared. 2 delta X.
Plus delta X.
Right? Okay. Minus X squared about that? Okay? Once again, the naked terms cancel. The x squareds, right?
Yes.
Every term left has a delta x in it, correct? So we can do the same trick we did last time. Limit, if I factor out a delta x, what am I left with on top?
Plus x.
Delta x squared.
Wait, why is it two? Delta x, so it's two x.
This is fine. Make sense? Focus. Okay. We're good? All right. So now these cancel, right?
Yep.
In the limit, I can now evaluate directly. In the limit that delta x goes to 0, what do I end up with? 2x. How about that? That's and that works, doesn't it? 2 times 3 is 6. But look what we got there. Let's call this f prime of x because it got changed from f of x. This is a notation for the derivative. So f prime of x equals 2x, and we have just invented a new function whose only job is to tell us what the slope of the curve is for any value of x. Right?
But it's
It is. It is. Okay, now I want you to, we'll do one more thing. I'm really hoping I can get this in. Let's graph these two things simultaneously. And I want you to see the relationship. Yep.
So that only works for the f of x equals x squared.
Yes, yeah, that was, we solved this problem for the specific case that f of x equals x squared. It would have been different, wouldn't it? If this had been, for example, if it had been x cubed. Then that would have changed this, f of x plus delta x then would have been that quantity cubed minus x cubed, and that expansion would have been a little different, right? We would have had a different result. Or if it had been like a sine x or something, right? We would have had to do something different maybe to solve this limit. Yes, sir?
So I can put this down as like f of 1x equals 2x when f of x equals x squared.
So so here's what we could say. If we started off with f of x equals x squared, then f prime of x, the derivative function, is 2x.
Okay.
Right? So if I asked you then, for example, what is the slope of this function at x equals negative 100, you would tell me that the slope is negative 200. That's very steep and negative, right? Yes, ma'am.
Wait, so is this just a coincidence, or does it work like you take the power and do that?
Okay. So there's one in every crowd. So the question was, is this just a coincidence, or is it, you take the exponent down in front, and it turns out it is not a coincidence? It's a little, there's a few other wrinkles that we have yet to discuss, but that is going to be one of our shortcut rules for taking derivatives for power functions. It's going to be different for other kinds of functions, like trig functions. I'll just give you one example. This is going to blow your mind. We'll prove this later. The derivative of sine x is cosine x. That's right. It is. So, which is really bizarre. You guessed, but you guessed accurately. We're out of here at 30, is that right?
Yeah.
Okay. I'll show mercy and we'll call her quits there. Yep.